All right, today we're going to dive into what I think is one of the most elegant, most beautiful experiments in the entire history of physics. It's the story of how one incredibly clever device found the smoking gun for one of Einstein's most out there ideas, and in doing so, it helps kick off the quantum age.
But think about this for a second. How do you actually prove an idea that you can't see, you can't touch, you can't weigh? How do you find real physical evidence for something that, up until that point, only existed on paper and inside the mind of a genius?
And that genius, of course, was Albert Einstein. He'd come up with this truly mind-bending idea that light wasn't just a wave like everyone thought, it was also a particle. Now, that's a concept that flew in the face of centuries of science. But see, in physics, a brilliant idea is not enough. You need proof. You need that smoking gun.
So Einstein suggested that all light energy comes in these tiny, discrete packets he called photons. This was his way of explaining this weird phenomenon called the photoelectric effect. Where shining a light on a piece of metal can literally knock electrons right off of it. It was a great explanation, but that's all it was, a theory, with zero hard evidence to back it up.
And that's where Robert Millikan steps in. Now, this guy was a master experimentalist. He was famous for being unbelievably precise. And the best part? He was actually pretty skeptical of Einstein's whole photon idea. So he took it on as the ultimate challenge. He would design an experiment to once and for all prove, or disprove, this crazy new idea about light. So how in the world did he do it? Millikan's big goal was to build some kind of device, a trap almost, that could measure the energy of a single electron that got kicked out by a single photon of light. I mean, just think about that for a second. Measuring the impact of one invisible particle hitting another invisible particle. The task sounds just about impossible. And that's the absolute heart of the problem, right? You can't just put an electron on a tiny scale or clock its speed with a little radar gun. Millikan had to figure out some indirect but totally ingenious way to figure out how much energy that little electron was carrying. Okay, so his device started with a pretty simple setup. You've got two metal plates inside a vacuum tube. You shine a light on one plate, the cathode, and that knocks electrons loose. Those electrons then fly across the gap to the other plate, the anode. When they get there, they create an electrical current. Simple enough so far. But here's where the genius comes in. Millikan adds a twist, something he called a back voltage. He basically rigged it so that the plate the electrons were flying towards, the anode, was now electrically negative. And since electrons are also negative, well, like magnets, they started repelling each other. He was basically putting on the brakes. This back voltage, this electrical headwind he created, was the absolute key to the entire experiment. Because now he had a dial he could turn that could push back against the electrons. And by doing that, he had a tool to precisely measure just how much energy they had. The whole process was so meticulous. First, he'd shine the light and get a current going. Then, he'd start to slowly crank up that repulsive voltage. And as he did, he'd see the current start to drop, because now only the fastest, most energetic electrons could power through that repulsion. He'd just keep turning it up and up and up until the current stopped completely. Zero. And that specific voltage, the exact point where everything stops, has a special name. It's called the stopping voltage, or V-stop. And why is it so important? Because it's a perfect measurement of the energy of the most energetic electrons. If you know exactly how much voltage it took to stop that fastest electron, then you know exactly how much energy it had to begin. So the beauty of this whole thing is this incredibly simple relationship. The maximum kinetic energy of the electron is just its fundamental charge multiplied by that stopping voltage. All Millikan had to do was read a number off of his voltmeter, do a quick calculation, and boom, he had the electron's energy. It's so elegant. But hey, one measurement isn't proof. To really put Einstein's theory to the test, Millikan needed to see if there was a pattern here. And this is where the experiment gets truly beautiful. He didn't just use one kind of light. Oh no. He used a prism to split light into all its different colors. He used red light, green light, blue light, even invisible ultraviolet light. And each of those colors, of course, has its own unique frequency. And for every single one of those frequencies, he did the whole experiment all over again. He would carefully, painstakingly measure the exact stopping voltage he needed for that color. This gave him a whole list of data pairs. On one side, a light frequency, and on the other, the energy of the electron it produced. So what do you do with all that data?
You plot it on a graph, of course. On the vertical y-axis, he put the electron energy that he measured. And along the horizontal x-axis, he put the frequency of the light that he used for that measurement.
And this was it, the moment of truth. What was this graph going to look like? Would the points just be a random jumble? Would they form some kind of curve or something else? Everything Einstein had proposed was riding on the shape these dots were about to form.
And the result? It was absolutely stunning. The data points fell into a perfect, straight, undeniable line. This was no accident. This was a clear, direct, linear relationship. The more you increase the light's frequency, the more energy the electron had, in a perfectly predictable way.
Now, a simple line on a graph might not look like much, but in the world of physics, this line was everything. It held the secrets that would confirm Einstein's theory beyond any shadow of a doubt. You see, this one line held three profound secrets. First, the slope of the line, how steep it was, turned out to be a dead-on match for a super important universal number called Planck's constant. Second, where the line hit the horizontal axis told him the exact threshold frequency, the minimum frequency of light you needed to get any electrons out at all. And finally, the y-intercept gave him the metal's work function, the minimum energy needed to just pop an electron off the surface. Okay, now check this out. This is the big payoff. On the left, you've got the basic equation for a straight line, which is what Millikan got from his real-world data. On the right, you've got the theoretical equation Einstein had come up with years earlier, based purely on his idea of photons. And when you put them side by side, it's a perfect mirror, a perfect match. The slope that Millikan measured was exactly Planck's constant, the h from Einstein's theory. The y-intercept he measured was exactly the work function from the theory. The physical experiment perfectly reflected the abstract idea. This was the smoking gun. This was the undeniable proof everyone was looking for. Millikan, the guy who started this whole thing as a skeptic, ended up providing the concrete evidence that yes, light does act like a particle. Millikan won a Nobel Prize for this work. And later, Einstein would get one for the very theory that Millikan proved. It's just an amazing reminder that sometimes the biggest revolutions in science don't come from some wildly complicated equation, but from a simple, straight line on a piece of graph paper. And it really makes you wonder, doesn't it? What other huge, profound truths are just sitting out there, hiding in plain sight, waiting for the right experiment to reveal them?